Okay, should work now. And then in passing, I will kind of give a few words about this Lean-MLIR project that developed in this group and how it's related to the ASA thing. So ASA stands for Instruction Set Architecture, and at least to me, it's a bit of a strange name, but basically it's like a contract between the CPU designers, such as like Intel or ARM or Apple, and the programmers. And kind of more concretely, it gives the semantics of the machine code that runs on the computer at a quite low level. So basically, it's in terms of bit strings. So basically, you have a bunch of bytes, which are your program, and then it explains how these bytes correspond to instructions, and it explains what happens when the processor executes these instructions. And because it's kind of a long-term contract, right? Like a program that was written decades ago should still run and have the same behavior on a modern CPU. This specification is kind of not totally precise, and it leaves kind of some leeway for the CPUs to evolve, which means that in PL terms, there is some non-determinism in the specification. And this is to contrast with kind of macro architectural details, such as, I don't know if you heard about this Spectre vulnerabilities, where basically you can think of the timing and how long instructions take to execute and so on. And this is not part of the ISA. Specifications are pretty large, right? So for example, for ARM, there's like 1,400 registers and around 2,600 instructions. So then you have like a big specification. It's kind of difficult to reason about them automatically. And just as a note, like in this work, we don't care about the memory model, which explains what happens when there is several cores executing at the same time and so on. We'll only focus on sequential code. So kind of what it looks like in practice, kind of historically, it's just a giant PDF written in English. So like, for example, this is the ARM specification, and you have around 14,000 pages. Yeah. It's like, yeah, with some English text. Oops. Yeah. Yeah, so for example, here you have kind of description, and then there's kind of preconditions that the index has to be a multiple of 4. There is what happens if the input is illegal or if some feature is disabled and so on. And then it explains how it maps to bits, right? So for example, this is how LD1W instruction is written as a 32-bit integer. But in addition, in most specifications, there is also pseudocode, which is more precise. So here this thing explains how to encode or decode the instruction. And then you have this kind of small imperative program that explains what happens when the CPU executes this instruction. And then kind of, I don't know, like a decade or so ago, Alistair Reed, who was a researcher at ARM, realized that kind of this pseudocode was almost a formal specification of the ISA. And so he created this ASL language, which stands for Architecture Specification Language, kind of which looks like the pseudocode ARM was using to make the specification formal, right? And so actually, this is like a formal specification with a compiler and so on. Yeah, and now he's working at Intel, and he's doing the same for the Intel architecture. Kind of in parallel, there is another language called Sail, which is developed at another group in Cambridge, led by Peter Sewell. And this one is used by the RISC-V spec, which is another kind of open source architecture. And this is the one we will use in this talk. And an important point is that these specifications are validated by the CPU makers against the internal test suits, so that we can have a good confidence that they are kind of match the actual behavior of CPUs. Okay, so like, why am I talking about this in the Lean workshop? Well, here we can give 3 examples of Lean projects that could use kind of a formal ISA. So the first one is called LNSim, which is developed at Amazon. And what they do is that they have kind of small cryptographic programs written directly in ARM assembly. And then they have a kind of handwritten semantics for ARM. And then they prove that because the little programs compute the right cryptographic functions. And then like if we could link this to the actual official ISA, then it could give like a stronger confidence that it's actually correct code. Another example, which is like the kind of the main reason why we did this project, is this ZKVM verification. So a ZKVM is like a virtual machine that, in this case, it executes RISC-V instructions. But not only does it kind of compute the result, it also computes kind of a witness that you can check that the result is correct and kind of comes from actually running the program on the inputs. And it's faster than actually running the program. So it's used in Ethereum blockchain. And the kind of main reason for our group to look at this is for verification of compiler backends. Right, because basically the correctness of a compiler only boils down to saying that the behavior of the source program matches the behavior of the target of the output of the compiler. And so for this, you need the semantics for the assembly. And so you need kind of a trustworthy semantics for the assembly. And so in our group, we have this Lean-MLIR project, which, as the name implies, is a kind of formalization of something called MLIR. So we'll explain what it is. So it stands for multi-level intermediate representation. And to explain what it means, I will kind of contrast it with kind of standard intermediate representations. So in the good olden days, the compiler took some high-level inputs, here, let's say C or C++, and then directly generated some assembly, let's say ARM, x86, or RISC-V. And then they realized that there's a lot of work duplication. And so they introduced intermediate representations. So the most common is LLVM-IR. And basically, you take your input program, you translate everything into LLVM-IR, then you do optimizations on it, and then LLVM compiles it down to machine code. Then they realized that kind of the semantic gap between C or C++ and LLVM-IR is very big. And so we added more intermediate representations. So for example, for Swift, there is one. For Rust, there is two, the high level and the mid-level intermediate representations. But what all these IRs have in common, that they can represent the whole semantics of the program, right? So that each mapping is very complicated because it has to deal with the whole complexity of the program. And because of this, like this, all these IRs are not reusable because they have to be specialized for Rust or for Swift or for C++ and so on. So in contrast, the idea of MLIR is that we don't use one IR at a time, but instead we use many kind of smaller specialized IRs that are called dialects. And then kind of a program is translated into kind of a graph of many different dialects. So for example, it's mostly used in the kind of machine learning compilation pipelines. Like for example, you have a dialect for math, which is like addition, multiplication, and so on. You have a dialect for linear algebra, for example, typically like matrix multiplications. We have a dialect for structured control flow. So it deals with, it has if then else and loops and so on. And then the translations between these dialects are much simpler, right? For example, going from linear algebra to structured control flow means that you kind of transform a matrix multiplication into nested loops, right? Which is like a very self-contained translation and very reusable because it can be used in many different contexts in many different compilers. And then usually at the end, you just compile this to LLVM-IR, which is kind of embedded as a dialect in the system. So kind of what this Lean-MLIR project does is that it kind of embeds MLIR into Lean. And so with the Lean metaprogramming facilities, there is like a parser for the MLIR syntax. So trust me that this is actually MLIR syntax as used by the MLIR developers. So this is a basic block with two parameters, X and Y, and then it just adds x and y, and then returns the result. And then what we would like to prove is that if x and y are just 1 bit, so booleans, it's actually the same as just doing an exclusive OR of the result, which is presumably a bit faster. And the goal is that it should be like the kind of lean overhead should be very small, so that kind of compiler developers and not lean specialists can use it. When you have this, it should be simple to prove that this rewrite is correct. So basically, we have tactics that kind of remove the MLIR LLVM kind of wrappers to get into the kind of mathematical core of this rewrite, which is just that if x and y are bit vectors of size 1, x plus y is equal to x XOR y. And for this, there has been a lot of recent developments in tactics from the FRO and our group. In particular, this BV-decide tactic, which kind of translates this into a SAT query and then use an external SAT solver to efficiently decide these problems. So that the idea that this type of simple optimizations could be proved automatically in a foundational way. And we also proved some kind of simple kind of classic optimizations, such as constant sub-expression elimination and dead code eliminations, as well as simple lowerings, which are like translations from a higher level dialect to simpler dialect. Okay, so what does it have to do with ISAs? Because before I said that in the end, all these fancy dialects, we just compile them to LLVM IR, and then we let LLVM get to it. But the thing is that sometimes it's not a good idea to go through LLVM because so much information, high-level information, for example, that we were doing matrix multiplications or whatever, is lost when you just compile to LLVM IR, which is very low level. And one instance of this that we kind of came across in our group, in the work by Sasha Lopukin and his colleagues, is that now there are these kind of new chips, kind of research chips that are specialized for ML workloads. So basically, they have like special instructions for linear algebra. But the thing that once we are at the LLVM level, you kind of forgot about which linear algebra operations you are doing. So it's very difficult to reconstruct the high-level operations. And so instead, they used MLIR and kind of embedded RISC-V, so the assembly, RISC-V assembly, into dialects. So here it's like the main RISC-V dialect, and this is like a helper dialect with the control flow, as well as the extensions of this chip, which is called snitch, and then directly do lowering from the high-level dialects such as linear algebra into these assembly level. So what we would like to do is to use the ISA, the RISC-V ISA specification to prove that this compilation is correct in this MLIR context. Okay, that's what's for the introduction. So now we'll explain more precisely what Sail is and how we translate it into Lean. So basically, this type of semantics are basically like it's a huge interpreter, which kind of explains what happens when the program is executed. And it's like a language with some special facilities to help write this strange type of programs. So in particular, there's what's called the scattered definitions, which means that the types as well as the functions don't need to be defined in one go, but instead you can add new constructors to types. For example, AST is the type of all the instructions. And here we say, oh, actually, there's an instruction which is called iType, and it contains these 4 pieces of data. And then we can also have functions that are declared across many files. So for example, we say that, oh, this decode function, which kind of takes 32 bits and say which instruction it corresponds to, can be defined in many different places in small snippets. And because we work a lot with bit vectors, there are special facilities for this. So there are these bit vector patterns. So this says that we name the first 12 bits of the word IMM, and then the next 5 bits are S1, and then the next 3 bits have to be 0, and so on, for this pattern to match. And then basically it's compiled into a giant match which combines all the clauses. Yeah, and then each instruction is really quite simple. So for example, this says how to add some constant IMM into a register. So what we say that we read the corresponding register, then you extend IMM from 12 bits to 32 bits, and then we compute the addition of the two, and then we put it back into the register, the destination register. And one thing to note is that there is side effects, right? Like we are reading a register and writing a register, which will impact how we translate this into Lean. And the other kind of big feature of Sail is that it has some dependent types in a kind of a strange flavor. So for example, here we have this fake function that has a kind of a type integer parameter n. It has to be positive or non-negative. And then it takes 4 parameters. So one is of type implicit of n. And implicit means that it can be omitted when you call the function. And the tic n means that the only inhabitant of this type has to be equal to n. So that if we give an explicit value, like 5, then the compiler will realize that n is equal to 5. So that's how dependency is achieved in this language. And then we can have some computation. So like we can say, oh, the second parameter is a bit vector of type 2 times n, and the third parameter is a bit vector of type n, and so on. And then to check that the type checks. So I mean, here is quite simple, but you could have commutativity and so on. Sail uses the Z3 SMT solver to check that the type parameters are equal when they have to be. Yes, so this is basically how you use Sail. So many specifications, as I said, are written using ASL, this ARM specification language. But then there is a translator from ASL to Sail, so that we have the ARM v9 specification Sail Morello, which is an extension of ARM, the x86 specification, as well as some specification kind of native to Sail, such as RISC-V. And here the stars denote the kind of the official specification. So this way, like kind of everything flows into Sail. And then from Sail, you can translate it into many languages. So you can translate to C, for example, if you want to run your model and test that is correct. To Verilog to do some hardware stuff, to SMT to do some kind of automated verification, and to many proof assistants, such as Rock, Isabel, and now Lean, which is the backend we've been working on. And our kind of the first target is to go from RISC-V through Sail to Lean. Yeah, so basically what we are doing is a shallow embedding of Sail into Lean, which means that we generate Lean functions and not kind of an IST inside of Lean. Kind of our principle roughly is that we don't want to re-implement the Sail type checker because it's very complex and it uses Z3, which is kind of an untrusted piece of software. We kind of want to get quickly to a minimum viable product so that we can start testing that it works well. And the kind of third goal in importance is to try to generate Lean code that's kind of beautiful, at least we are trying. Yeah, and then we work directly upstream. So everything I'm showing you is already in the Sail Git repo. Yeah, and there's we have reasonably good practices. We have tests and stuff. Yes, so like this, to not re-implement the type checker, we have this slightly cursed coercion, which says that if I have a bit vector of size n, but Lean wants a bit vector of type m, we just change the width, and we hope it never happens. Right, so we hope that whenever this instance is called, n and m are not necessarily definitionally equal, but they will be equal. Another problem is that in Sail, the type level numbers, the tic n that we are seeing, are integers and not natural numbers. So we have this other coercion which says that if we have an int and we want a nat, we just do two nat, which kind of has this mean of 0 and the actual integer. And the hope and the idea is that anyways, we want to prove things about these models. And so like we have to prove that things kind of match up. And so it's okay if we have kind of basically the verification is stronger than type checking. And so anyways, we will have to do this work. So it should be fine to do these coercions. And then for all the kind of other features that I've shown you, like the clauses and so on, scattered definitions, Sail can compile them away in its internal representation. So for example, if we have this function with two clauses to decode like two instructions, we generate this code, which is not ideal, but okay. All right, so basically we have this first pattern, right, which says that basically these 3 bits have to be 0, and these 7 bits have to be this pattern. And this is transformed into an if. And if it says that, oh, if we take these 3 bits, they have to be 0, and the bits from 0 to 6 have to be this pattern. Then we name the sub-branches, and we return, and so on. But that, of course, the problem is that it can create very large functions. Yes, and then the last thing we had to do is interpret effects. So basically, we have a monad, kind of generic monad that we write once, which we call pre-sail M. And it's basically an exception monad with a state monad. And then there is some sequential states in the states, which contain the registers, which are used as which are a dependent hash map. And here, the type of register and the contents they have is a parameter. And then we have also the state of the memory. And then once we generate for a concrete model, we kind of instantiate this generic monad with the actual register type and exceptions and so on. Yes, so like our kind of first milestone is to compile the RISC-V model. So when I wrote this slide, it was 80,000 lines of Lean. I think since yesterday, they did some change in the model, and now it's 100,000 lines. Now I think VS Code is not happy. Yeah, and then there's this, we have this large type, and the BEQ instance takes 2 minutes to compile, which is not ideal. And there's still one error for the some loop, but we know what's wrong. So this is what it looks like. Yeah, so some parts are good. So like, for example, this execute I-type, which is how to do kind of arithmetic operations. It's quite readable, right? Like you match which operation you want to do. Let's say we want to add 2 numbers. Then we read the register. Then we have an arrow because it's effectful. Then we add the immediate bit vector. Yeah.
When you say some tests pass, just from my own understanding, what's an example of a test in Sail? Like, is it just that, I don't know, addition leaves things in a register that are actually the sum of 2 things, or is it more about that there's no conflict in the mapping space of the instructions? Like, what are the actual tests?
I think so. These tests are more like very small tests for kind of language features. So it would be like the first, like you take the registers, you add stuff, and you check it's equal to. Yes. So like this is, I think, quite readable. But then you have, yeah, like this part. Yeah. Which is basically the thing I was showing, right? Like you have, I don't know how many instructions, like, yeah, so this AST is like, I think like 130 variants. And so then you have 130 nested if then else function. And then I guess in ARM it would be much bigger, so it's very bad. Yeah, so we have kind of a match for bit vectors, which can have the same type of patterns, which would solve this, but we need to support when clauses to use it, so it will be better soon, hopefully. Yeah, so then we are like 8, yeah, most of the way there for the test suits. Okay, so what's our plan for the future? So first we want to finish the RISC-V model. Then we want to try to use to do the ARMv9 model. And then we want to do good kind of thorough testing of the model by kind of compiling this into this Lean model into executable code, and then execute binaries. Yeah, and for this, we hope the new Lean compiler will work, because the current compiler doesn't terminate or crashes, I think, for the biggest functions. Yeah, and then we want to explore kind of techniques to simplify the model for user code, because most of the complexity of the models are for what the operating system can do to interact with the CPU. So for example, I tried to kind of color code like in the table of contents, like the yellow part is the user model, like what you use when you write a program. And then the red part is like the systems part, and it's like much, much bigger. But you have to deal with it. That's the problem, because it's part of the model. And when you want to reason about the model, you have this 1,000 registers that you don't care about. So we want to use, try to use kind of symbolic execution and so on to get rid of it. Yeah, and then as we said, we want to connect the model into the existing projects that use ASAs, but kind of handwritten specifications. Yes, so we hope you will find this project useful. So both directly as if you care about ASAs, but also I think it can be a good test bed for kind of doing automated reasoning in Lean. And so as a simple exercise, I was curious, like, like Sail uses these three for type checking. Like, okay, like, can we prove these queries using Lean automation? So I just generated a Lean file with all the queries. It's like a few thousand. And with like simple automation, just grind and simple and omega, like 98% work are proved. So I was quite surprised, happily surprised. Yeah, that's it. Thank you.